Have you ever stopped and thought about how wild it is that a machine can just look right through you, see your bones and everything? It feels like something out of a comic book, but it's not magic. It's all physics. So let's get into it and break down the science behind one of the most important tools in all of medicine.
Okay, so really, how does it work? I mean, think about it. You've got this invisible beam of energy that just sails right through your skin and muscle, but then, bam, it gets stopped cold by your bones. And somehow that creates this perfect picture of your skeleton. That's the big mystery we're going to solve right now.
To get to the bottom of this, we've got to go all the way back to 1895. And believe it or not, it all started with a total accident. A physicist named Wilhelm Röntgen is just tinkering in his lab, right? And he notices this weird glow coming from a screen across the room. He figured out he'd stumbled onto some kind of, rays of mysterious origin. And since he had no idea what they were, he called them X-rays, X for unknown. And get this, just a few weeks later, he takes this picture. It's the first ever X-ray of a person, his wife's hand actually. You can even see her wedding ring. And just like that, medical imaging was born. Okay, so that's the origin story. But how do we get from Röntgen's lab to the sleek machines we have in hospitals today? Well, for that, we need to pop the hood and see how these X-rays are actually made from scratch. All right, before we go any further, let's do a super quick Physics 101. Remember atoms? They're the tiny building blocks of literally everything. You, me, this screen. The easiest way to picture one is like a little solar system. You've got the nucleus in the middle, kind of like the sun, and then you have electrons zipping around it in orbits or shells. And trust me, this simple little structure is the key to everything we're about to talk about. So X-rays aren't just any kind of energy. They're what's called ionizing radiation. Sounds complicated, but all it means is they pack enough punch to literally knock an electron right out of its orbit. It's like a tiny, energetic cannonball. And this one little action, ionizing an atom, is the secret sauce. It's how the image gets made, and it's also why we have to be careful with them.
So inside that X-ray machine, there's this really cool three-step dance that happens in less than a blink of an eye. First, a tiny wire, a filament, gets super hot and basically boils off a cloud of electrons. Then, step 2, a huge jolt of electricity fires that cloud of electrons across a tube at an insane speed. And finally, step 3, bam! They smash into a metal target at the other end. All that energy has to go somewhere. Most of it, like 99%, just becomes heat. But that last 1%, that's our X-rays.
And how that impact actually makes an X-ray is pretty wild. The best way to think about it is like a Formula One car slamming on the brakes. As one of those super fast electrons flies past the nucleus of an atom in the target, the nucleus's gravity kind of pulls on it, forcing it to swerve and slow down hard. All that kinetic energy it just lost has to go somewhere, right? So it gets shot out as an X-ray photon. And this braking radiation, as it's called, is where most of the useful X-rays for our images come from.
Okay, so our X-rays are born. They're flying out of the machine. Now comes the most important part of their story, the journey through you. This is where the real magic happens.
Now, when one of these X-ray particles, or photons, hits an atom inside your body, one of two things is probably going to happen. It can either be completely absorbed. We call this the photoelectric effect, but you can just think of it as a full stop. Or it can hit an electron and bounce off in a new direction, kind of like a billiard ball. That's called Compton scattering. And here's the deal. For a nice, crisp image, we love the full stop. The ricochet stuff, that just creates noise and makes the picture blurry.
And this is really the whole secret right here. That photoelectric effect, the full stop interaction, that's what gives us the amazing black and white contrast we see in an X-ray. And what decides if an X-ray is going to stop? It almost all comes down to the atomic number of the atom it hits. Basically, how heavy and dense is the stuff it's trying to get through. And this chart just lays it out perfectly. Look at bone. It's packed with calcium, which has a pretty high atomic number. That makes it an X-ray sponge. It's really, really good at absorbing those photons and making them full stop. But then you have muscle and fat. They're made of much lighter stuff like carbon and hydrogen, which have low atomic numbers. So X-rays tend to pass right through them. And the result is exactly what you see on the film. Bone shows up as bright white, and the soft tissues are all different shades of gray.
All right, so we have this invisible pattern of X-rays flying out the other side of your body. Some made it through, some didn't. How in the world do we turn that invisible pattern into the picture we can actually see?
Well, there's a fancy science word for this whole process, attenuation. But don't let it scare you.
It just means the X-ray beam gets weaker as it passes through stuff. Why? Because some of its photons are getting absorbed or scattered away. Simple as that.
So what comes out the other side of you isn't the same strong, uniform beam that went in. What comes out is a pattern. It's basically an invisible shadow of your own insides. The parts of the beam that went through bone are now really weak, and the parts that went through your lungs or muscle are still pretty strong. You can think of the whole thing as creating a shadowgram. The machine fires the X-rays. Your body casts an intricate shadow based on how dense everything is, and then a special detector, sitting right behind you, catches that shadow. It's like a high-tech piece of film. That detector measures how strong or weak the X-ray shadow is at every single point and turns that data into the black, white, and gray image we all recognize.
Okay, let's circle back to that word I used earlier, ionizing. Because the same power that lets X-rays see through us is also the reason we have to be really smart and careful about how we use them.
Remember how we said X-rays have enough power to knock electrons out of their atoms? Well, that's not just how they create the image. Every time that happens, a tiny bit of energy gets left behind in your body's tissues. And that leftover energy, that's what scientists call a radiation dose.
So to really understand what that dose means, we need to put it in perspective. We're actually bathed in a little bit of radiation all the time. It's called background radiation, and it comes from space, from the rocks in the ground, even from the food we eat, like bananas. On average, just by living your life for 1 year, you pick up about 300 units, or millirem, of this natural radiation.
So, keeping that 300 number in your head, let's look at a common medical X-ray. A single chest X-ray gives you a dose of about 4 millirem. Yeah, just 4. When you stack that up against the 300 you get anyway just by walking around, you can see we're talking about a really, really small amount of extra exposure.
And this all leads to the golden rule in medical imaging. A doctor is only ever going to order an X-ray if the information they're going to get from it, confirming a broken arm, finding pneumonia in your lungs, is way, way more beneficial than the tiny, tiny risk that comes with the dose.
It's pretty amazing when you think about it, right? From a complete accident in a dark lab over a century ago, to a tool that's now a cornerstone of modern medicine. X-rays give us this almost superhuman power to see the invisible. And that leaves us with a really important question. How do we continue to balance the incredible benefits of this life-saving technology with its potential risks, making sure it keeps helping people for the next 100 years?